Hi, my name is Sai Nelaturi. I am a research area manager at PARC, and I manage a group called CASE, that stands for Computation and Automation for Systems Engineering. And in my group, we solve a lot of applications in engineering, design, and manufacturing that deal with automated reasoning of complex processes during engineering design and fabrication planning. Some of these applications involve things like collision detection, spatial planning, packaging, manufacturing analysis. We basically try to look at where engineering software can provide much value to human designers in order to be able to make their workflow easier in designing complex problems. One of the projects that I'm working on right now and I'm most excited about is called Fields. And this is a project where we are trying to rethink the foundations of CAD and really build the future of computer-aided design, manufacturing, and engineering analysis software. This project is funded by DARPA, by the Defense Sciences Offices, where they're thinking about how to harness the capability of modern manufacturing systems, such as additive manufacturing systems that can work with multiple materials, and yet be able to deal with the complexity enabled by these systems that are simply not there in computer-aided design systems today. So to be able to handle this complexity of manufacturing processes, we think that the assumptions underlying computer-aided designs have to be rethought and have to be reformulated to really match what is state-of-the-art manufacturing today and for future manufacturing systems, as opposed to the assumptions that are built into CAD systems today, which were aimed primarily at state-of-the-art manufacturing in the 1970s, also called CNC machining. CNC machining continues to remain an important manufacturing process, but is now augmented by other processes like additive manufacturing. And to be able to truly exploit the capabilities of these systems, we have to introduce design optimization, manufacturing planning, and engineering analysis, all working tightly together and harmoniously in order to provide human engineers a collection of solutions which they can explore and curate in order to really design next-generation state-of-the-art products. So one of the really interesting things we are doing in the Fields project is connecting the designs and the representations that we are inventing to manufacturing capabilities. And 3D printing is a very attractive use case because now you can actually print very complex shapes with multiple materials. So as an example of demonstrating what we are doing, here's a cross-section enlarged of a human femur that shows multiple materials towards the outer structure of the bone, as well as the microstructure on the inside that you can see has functionally graded material properties. And to model and represent this and even 3D print this takes quite a bit of hacking of both the 3D printers as well as the softwares that are used to control them. So because today this kind of complexity is not really supported by 3D printers directly or natively, if they were using input, say, from a CT scan, very few printers out there can actually handle this complexity. Now, but if we are able to create a design system that not only does the design optimization and allows you to do the editing, but also connects it to manufacturing process planning, and then finally to create manufacturing instructions to a 3D printer, we have an end-to-end system for design and manufacturing for next generation products.